That's what you should be there. Okay, then we'll go beyond to what we have been saying last time in terms of the particle size and things like that. We have to now slightly go more into the particle sizes. The reason is that particle size is not uniform, unfortunately, and there will be a lot of variability there. So we will spend some time on to the interpretation and to see really how the data in atmosphere really look like. Okay. The particle emissions from both man-made and the natural sources do not consider a particle of any one size. That's what we said, because last time we were just sticking to one particle. Okay. Instead, they are composed of particles of a relatively wide size range. It is often necessary to describe the size ranges. Particular particulate matter for size distribution evaluation is measured in a variety of ways. We have to give the size distribution, like what is the mean of particle size and what is the standard deviation of particle size and things like that. Cascade impactor. Have you heard about the cascade impactor? No. See, what happens is, because when it comes to the matter of interest, either as when you are controlling the particulate matter, or you are trying to see what are the particulate matters in the atmosphere. Okay, and size is very, very important, especially because of the health point of view, and also the way you have to design a system. Then you want to design a system which particle size you want to remove. Okay, so therefore the system which is somehow segregates the particle size is try to use the advantage of something like called cascade impactor. Okay, it is based on the inertia. Okay, what happens is, suppose I have a plate here. Okay, and my airflow is coming onto this. Okay. Now the particles, and then we have the particles of different sizes, some small, some big, some small, and many are small, and some may be big, most of the big particles. Okay. All the particles as well as the gas stream both has inertia, right? Okay. Who has more inertia? The particle has much larger inertia, whereas the gas has no inertia. Okay. So gas, since they have no inertia, so they will continue to, the gas streams will try to turn and follow this, we go beyond this plate. Okay. Now, even amongst the particles, which will have the more inertia and which the larger particles will have more inertia, right? So the larger particles, what they will do is that they will tend to separate out from the stream because they have the inertia, so they will try to travel in the same direction. Okay. Whereas this small particle which you see, it will escape, or it will try to go along with the gas stream. Okay. So you see the larger particle which you see here, it goes and hit to the whatever plate you may have. Okay. It may head to the plate. And then to capture this particle, you may sometimes, if you wish, you can put a little oily surface. Okay. So once it's hit, because you want to separate out these particles, that hits, and the smaller particles, like for example this particle will continue to move out. So this particle, the smaller one, will continue to move out along the gas stream, and then larger particles will be stopped, just based on the inertia. And then I can have a filter here, and then I'll see all my fine particles. Okay, that will be collected here. So I can separate out. This is called cascade impactor. It's cascading effect. Then it can go to here. If I want to further fractionalize that one, I can make it further. Okay, then the further kind of plate, so that some particles will stay here, some will continue to go down. So I can even find the particle size distribution. And sometimes the same kind of concept I use while controlling certain particles. Okay, and sometimes measuring the particles in the ambient air. कैसे impact the particulate matter is separated into the diameter size category within the impactor head during the sampling. The mass of the particulate matter contained within each size range is recovered and determined grammatically. Now you can measure these particles or you can measure these particles, and you know then most of the equipment what you see will be, like for example, PM10 analyzer, PM10 sampler basically. Time permitting, I might show you that picture also. So in PM10, so all the larger particles will stop and only PM10 particles will be retained here. Okay, the particle size less than 10 aerodynamic diameter. You can do the calculation, you can design the things because you know the inertia, you know the general structure of your particles in the atmosphere. Particle count is also the very important thing. Some of the medical people prefer not the mass but the number of particles that are there. There is another method to data interpretation for the size distribution. I will show you the figure 1 in a moment. I will show the fly ash collected on a filter paper. The filter paper material also depends on to what kind of material you have, and the larger reason for a particular type of material where you have the filter paper can be many reasons. Okay, sometimes suppose you are doing a sampling inside the stack, okay, and you know cellulose is very ordinary paper, cellulose, right? Okay, and suppose the stack temperature is high, and you have made very sophisticated sampler that you only want to sample the PM10 particles coming from the stack. Okay, what will happen? This particle in the stack, the temperatures could be high, right? This will cellulose will completely burn out. Okay, you will say, oh well, you didn't get anything. Okay, in that case you may like use to Teflon. Sometimes you are doing, suppose very sophisticated, you want to find out the metals in the atmosphere. Okay, so suppose the filter paper where you are collecting itself has a lot of background heavy metals or metals, then it becomes a little problem. Okay, because the background pollution will be interfering so much with your actual thing which you want to measure, so then your choice of filter paper can be different. Okay, for example, well, we are drifting, but that's fine. You want to measure the silica, okay, and suppose you are using the quartz filter paper, you will never be able to find silica in the air if you are using a quartz filter paper, because quartz is all 90% silica, and then you will never be able to find. So that also decides as to what kind of filter paper. It depends not on the particle size, but in what way you want to characterize the particle. So that also decides the filter paper. The particles shown will in the figure are size range 1 to 5 micron. From the picture will show the number of particles in a predetermined size range is tabulated, and that I'll show in figure 2 in a moment, because that's how we analyze the data. So here what you are seeing here is the white dots you see are the fly ash particles, okay, and these are the filter particles, or little black you think. So when you look at the microscope, you can see these particles, and in fact you can also determine the particle sizes through some of the equipments. What they do, some of the equipment, I'm forgetting the name, they will see the particles, okay. They make some kind of fringe, the machine, through the lights and the mechanism they have, and then that particular size of the fringe along the particle is measured, through electronic means and something like that. But the other way to show the data, okay, which we are getting the particles, because we need to say, well, maybe sometimes the interest may be in the larger particles, okay, then you want to say how much quantity is the larger particles, because you have to design an equipment sometimes, okay, for a specific particle size. Maybe you want to just remove these particles. So the loading can be different for the larger particles, smaller particles, and this thing. This is simply a frequency plot for the by percentage by counts, it says, okay. The number of particles, okay, that by counts, that will be in that category. The particle diameter, and then obviously we know that, well, here we all understand mode, we understand the median, we understand the mean. There's nothing new about this one. But I think what you need to understand from here is, suppose you have a very wide range, okay, and not quite wide. Let's say you have something like 1, 1, 2, and then you have 3, 3, 4, 4.5, and 5, 5.5, and you have another one data point is 30 and 15. Okay. You have to be a little careful sometimes. What you want to take is you want to take the mean or the median here, because you want to find out the average particle size. Okay, so you have to be careful sometimes that you have to, in such data set, you have to take the mean, you have to take the median, because that is much robust central point rather than this thing. Because you see, you can see these points which are really not quite there, but they will influence your arithmetic mean hugely. Okay, and sometimes we make wrong decisions and we say, oh, or most of the particles are sitting somewhere at 7, and you see we have no particle at 7. Okay, not even factor one single particle, because average may come out to be 7 because you have the large numbers here. So, but if you take the median, you can suppress the effect of the large number of observations and things like that. The other thing which you need to see it quickly is the skewness of the curve. Okay, okay. This is skew to left or skew to the right? Skew to the right. Okay, always remember, because it has the extended tail onto the side, so it is skewed to the right. Okay, and such the curve, and why we are mentioning here is, in fact, most of the time, 99% of the time, when you look all the environmental data, not only in air pollution but in water pollution, soil pollution, when you have these number of measurements, okay, when you plot them, this thing, you will find that this data to be skewed to the right. Okay, and such distribution, obviously this is not the normal distribution, and in fact this is what we call as the log normal distribution. We should a little bit be aware of that, because data are skewed to the right. Okay, so that is a skew thing which I wanted to show, and obviously the other way that I can plot the same graph is that I can take the logarithmic of these values, and that's what has been done to show that this data, well, not quite anyway. Skew distribution shown in figure 2 typically encountered in the field of air pollution control. Not only air pollution control, even if you have the data from the water pollution control. Okay, any guess as to why the data will be log normally distributed? One of the reasons is that we are not likely to get negative numbers. Okay, so as a result, the things are the tendency towards the right side, and that's why the data always skewed to the right. The median arithmetic mean, we all understand that mass median particle diameter is the particle diameter that divides the frequency distribution in half. Okay, the arithmetic mean, we all understand and the mode is, of course, most frequently encountered particle. But then what I really want to show this, so what you understand is it is the right time to discuss this. The same data set, okay, but what you see here is that we have taken the logarithmic here, and then you see the distribution become very nice, and everything tend to more or less coincide, mean, mode, median, and this is how we want to sometimes distribute the data. So in fact, whatever the analysis sometimes we need to do in the field of environmental quality, normally we should deal and treat the data log normally. Okay, because if you do something normally, there will always be a question in the exam or something that, or you're writing a paper, they'll ask you, oh, why this data is taken normal. Either you establish, okay, the data was normally distributed. If you don't want to establish, I think it is reasonably safe that you assume that data to be log normally distributed. As shown in figure 3, the particle size categories are altered to produce equidistance range when they plotted on a logarithmic basis. This bell-shaped curve is log normal curve. It may not be perfect, like you've shown for some data and this thing. And the entire curve, okay, when you have this kind of distribution, can just be defined, okay, and by the two variables, mean and the variance. Okay, you all know about that one. So you can find out the mean and variance, and normally what is written, okay, I want to describe the whole data set, okay. I'll simply write, suppose this is normally distributed, for example. Enough for me to describe the whole data set. Okay, you just write that it is normally distributed with mean mu and the variance sigma square. Okay, and sometimes, or maybe, or you can say it is log normally distributed with mu and sigma square. Okay, some people prefer, because log normal or geometric mean, some people prefer to put it z here or put z. Enough to describe the entire data set, okay. How to find out the mean and variance, all this one but the other ways to find out, sometimes we use we'll quickly define those terminologies, because we might use it sometimes, when we are talking about the control technology. Okay, the geometric mean diameter is the geometric standard deviation are substituted for the arithmetic mean diameter and the standard deviation when incorporating the logarithms of the number. Okay, you can find out take the log of each of the particles, okay, and then take the simple arithmetic average, but that what it is giving you is the log dg, and what I am interested in the geometric mean. So that is what is you get the geometric mean. This you can come from here to here. Okay, the interesting thing which I want to share with you is suppose use the observations which are a little widely distributed, okay, 3, 5, 9, and you find out the arithmetic mean. Okay, I don't know what will be the arithmetic mean, but if you take the logarithmic mean or geometric mean, what difference you expect in these two numbers? They should be somewhat similar, of course, because they are both are trying to measure the same thing. Okay, but you will see here this the impact of the larger values is kind of suppressed. Okay, and that sometimes is better than using this thing, because if you have the data to be distributed, you expect some numbers to be more onto this side, and then you see it is compressing. So sometimes while explaining the things, and when trying to get more accurate number, the geometric mean is better than the normal arithmetic mean. Okay, there is another thing which we sometimes want to define, okay, which I am not writing here, is the coefficient of variation. Okay, this is your standard deviation divided by the mean. Very simple thing, but very useful thing. Why useful? As you see here, the sigma gives you the variability in the data. Okay, sigma gives you the variability in the data, and sigma, what units it will have? It will have the same unit as x, right? Okay. So suppose I am comparing the variability, let's say we are just drifting, let's say we talk about water pollution further. I am comparing the variability in terms of the BOD and COD, okay? Or let's say we are comparing, what should we say? You are comparing, let's say, between BOD and pH, okay? The measurement of BOD is in milligrams per liter, okay? And that can vary from whatever 2 to 2000, and pH will vary in narrow range, and the units are different. Okay, but you want to say about the data that, well, which one is more distributed? Where the more distributed, you have the less confidence in the measurement, because you don't know whether this is this or that. So what you can do is that you, for any data, you can find out the coefficient of variation. Okay, and the coefficient of variation becomes dimensionless, and then you can compare anything versus anything. Okay, anything versus anything. Another little tip, it is not, it's more like thumb rule, or more by the experience it has come. You can also try this one generally. If is less than 0.5, you would expect data to be normally distributed, generally. Normally distributed. Okay. Sometimes we also need to find out the mean and variance. We sometimes, on purpose, we find out through graphical method rather than using on your calculators. Okay. What you do is use the graphical means, and I think I probably have the slide here. Okay, let's do the example where you want to find out the mean and standard deviation. And I'll tell you, under some particular situation, we can only use the graphical methods, and you cannot use your calculator unless you want to write a program for something. So understand, because this is what we encounter this situation many times, and we should know the basics. Example 1 is we have to calculate the mass median particle diameter and the geometric standard deviation for the particle size distribution, which is given here. Okay. You have the size range, okay, micrometer 0 to 2, 2 to 4, 4 to 6, 6 to 10, and this is the aerodynamic diameter, which is at the minimum one. Okay. Normally we plot the things based on at this minimum level. Okay. What was the mass concentration or the mass value or concentration, doesn't matter. So concentration, okay, of the particle in the range was from 0 to 2 was 1 micron per meter cube, and this was 2.4 plus 14, 24.7, 59.8, and this and this and this. Okay, so it can reduce also. Okay, now what you want to do is that the mass size in the range. Okay, so what have you done here? Now you're looking at the mass. Okay. Okay, how you will get this number? Simply by dividing by 2, okay, in that range. And then you want to plot the cumulative thing, so you can find out the cumulative here is 0.5, okay, cumulative here is cumulative 0.5 plus 7.25, 7.75, 7.75 plus 12.35 is 24, this thing. And now finally what I want to plot is this versus this, okay, and it will become a straight line. The provided data is distributed. Okay. So we wanted to find out the geometric mean and geometric standard deviation. So what I would do is the particle size is plotted on this side. On this is on what we are plotting micron meter, but on the logarithmic scale, right? Okay. And the cumulative mass fraction, that also is on the log scale. Okay, when you provide both the things on the log scale, it becomes a straight line. Okay, so now what you can do is that once you have plotted this, for example, if you recall, what was the range? The lowest range was 2, corresponding to 2. What was the mass concentration? 0.5. Okay, then we went to the range which was like 4. About 4, it was something like 12 point something. Okay, you go from here 4, and then something like, well, this is a point. What was that? 12 point something, right? 7 point something. Oh, I'm sorry. 7 point something. So you probably will get 7 point something from here, and so forth you can do. And what you can do is that if you at the 50% D50, okay, where the 50% of the mass, okay, is there, and so that will be your geometric mean diameter. You can find out. So this will be like the particle size 10 micron is the geometric mean, and then if you go 15.78 and 84.13, okay, you will get the value of standard deviation. Okay, you know why it is standard deviation? What was that? Let me also recall here. Okay, and we're plotting the cumulative. This is not cumulative, this is simply frequency plot. So that's one standard, and this, the area, how much is this area? Anyone remember? 60 something, 68 or something? 68? 68%. So this will be like 50, and then this will become how much? So this, can we find out or can we not find out from here? 16 something? 15.78. Okay. This is a simple thing, of course, but important thing, we should make it a habit, we should make it as a practicing engineer. Every time we need to do this. Like it's not all the time you're solving huge equations and things like that. Most of the time you probably will deal with this thing. So you can find out the standard deviation. Okay. How do you find out the standard deviation? But is see here, now you can find out the geometric standard deviation. Take the value of d50 divided by this thing. Okay. Why would that be? Why division? Because there is a logarithm terms, right? We had this, what were the observations we were getting with the logarithmic values. So you divide this by, either doesn't matter, by d50 to do 15 by 7/8 or d84.3 by d50, and you will get the geometric standard deviation of the particles of mass distribution. This is your mean, and these of course are corresponding to your 15.78 and 84.13. The other thing which I wanted to tell you was, let me think. Okay, any measurements that you have and you're plotting some like cumulative thing. This is the simplest thing I'm telling you. There are more complicated things. Handling and weave. Handling the data below detection limit. As environmental people, as an environmental engineer, it is very challenging that you will do some measurements and the data are below detection limit. Okay, and then you can't ignore those numbers because that is the information, although it may be incomplete information. Okay, suppose you are doing some measurement. Okay, let me say, suppose you are measuring, let's say you are measuring mercury, for example, and your instrument capability and things like that was your minimum detection limit, let's say 0.5 nanogram per liter. Some of the observations were this, some of the observations were higher. Then how will you utilize this information as well? Okay, that becomes tricky. So in that case, what you do is you plot the data. Okay, plot the data as the way we have seen it, and of course in this range, okay, you can't plot the data. Okay, and you're measuring x and y. Okay, there was something you are measuring and then some response. So what happens? X is generally easily measurable when you are plotting x and y. Y is a response. Okay, so suppose you could measure this. Okay, and then you, for this corresponding this value, when you measured the mercury, let's say this was your wind speed, for example. Wind speed you can measure easily, but when you, for that wind speed you measured the mercury, and then your instrument said below detection, below detection. So you can plot the things on the x direction. Okay, but you don't know what will be the values here. Okay, because your instrument said less than 0.5. So it doesn't mean the value is 0.5. It doesn't mean the value is 0. It doesn't mean value is 0.25. Well, we don't really know where the value is, but still we don't want to throw this information, nor we want to use it improperly. Okay. I want to tell you a little story about that. But let me see what all needs to be covered today before we go to the story. Serious court case in US. It was landfill. Okay. This is the flow direction of water. Okay, then they have the bore wells, okay, and they'll take some observation because of the leachate pollution. Okay, they're saying the well, this landfill is polluting the groundwater. Okay, so they'll take some samples here at the upstream and take some samples at the downstream. Okay, so they took the measurement 1, 2, 3. They took the measurement 1, 2, 3. Industry, which is landfill company, versus the company or the regulatory agency which they want to. They are saying that you are polluting. Okay, and then suppose this data were less than 0.5. for example, okay, and now the company said that please take this value as 0, okay, because they wanted to lower the impact. Okay, the regulatory agency said, well, we'll take this equal to 0.5. Okay, there are more data points. I'm just cutting the story short. So then it became the problem as to how what the value of x2 should be taken as, because it's anyone's guess. Okay, it can be very close to 0.5 or it can be very close to 0. And it means huge implications. You see, this could be closed down, this could be fined, the person could be imprisoned because, like they are polluting, etc., etc. And same thing. This kind of problem can also come into the forensic measurements, like the DNA and things like that, like some problem somewhere in the measurement and things like that, lower than this thing, or, they have some information but incomplete information. So one of the simplest way I'm telling you how to handle these things is that whatever the good data points you have, you plot, okay, and then whatever this line you have got, this line, okay, because you know the data will be log normally distributed, and that you have established with good data that they are log normally distributed. Then what you do is you extend this thing in the same slope, okay, and then for this you can estimate a number. Still, God knows what is the true number, but still it's a much scientific way to estimate this missing number or missing data than doing it, like half of the lower level plus the higher level, or taking the higher level. People to their advantage will like to make something. Somebody will say, well, please take this equal to 0.5. Somebody will say, oh, you should take 0. Or somebody, like, who knows little science, they said, well, please take 0.25. But none of them are correct. But still, so there's still many complicated statistical ways are there to handle these, but this is the simple thing. You could measure the x, but the y response you did not get through your machine or equipment what you had. But the rest of the data points were good, provided. You can't say all the data were below detection and then you could still improve on that. You can't. So with this thing, because this, that if it is following some kind of distribution, it will continue to follow in all likelihood same kind of distribution. So for this, you go here, find the response y1, y2 for this data which are below detection, and then use these numbers, okay, finding out the overall average, mean, standard deviation, whatever you want to do. Okay? It is the same thing what we did, and then you go, same graph you go with this ratio of D50 to do 15.78, it'll be the more or less the very, very close to the same thing, provided your distribution was, like bell-shaped and normal distribution. Well, we'll leave that graph for the moment. Sometimes you will find that some of the graphs are plotted, and then you should approximately understand that why they shape the way it is. So here what we are plotting here, the number concentration, and here what are the units, probably at the back you can't see, they are really in the nanometers. Okay, when it comes to the number particles on the higher side, like this will be what size this particle is, 10 to the power 6 nanometer will be what? 1 mm or something, or you reduce this one. You can find out, basically what is the big deal. 10 to the minus 6, 10 to the minus, what is that? 6 nanometers, so you can say into 10 to the power 3, this is a micrometer. Can we say that? So you can find that one out, but what you see here, the smaller particles, what you see, the particles are smaller, they are more in number. So, okay, so you have to see the graph, then whether you are talking about the mass or the number. And if you look at the mass, the distribution is entirely different. More mass comes on the larger size particles, and the numbers are somewhere here, large number, almost insignificant number which is there. So depending on what you are using it for numbers, because these some of the medical doctors will prefer a number concentration rather than the mass concentration. But in environmental air pollution, we mostly need the number concentration, the mass concentration. So here you see change in the mass with respect to change in the diameter on the logarithmic scale that is plotted here, and typically in the we get this kind of distribution. Okay, so you get the bimodal distribution. One are the sources of the particles which are generated more from the mechanical operations. Okay, and these are the which are come out more because of some of the processes, and those processes are happens in the atmosphere, this kind of thing. Okay, you should understand. Okay, here are anyway these are the wind blown dust, emission, sea spray, volcanoes, and the particles more of the grinding kind of things, soil dust and things like that. So you have the large particle range here. Whereas when you are the finer mode particles, they are formed rather than you can create them really, through the mechanical devices. So here you have the gaseous vapor, okay, where you have very high vapor, lots of the concentration is super saturated. Obviously the condensation will occur, and then you have it will make the primary particles, and they can very small particles, very small particles. They can come and they can coagulate and make slightly larger particles. But the other thing which happens very quickly, okay, if you have the other particles present in the system, they can act as a condensation nuclei, and the particles the vapor can condense on them, and then as a result, even if the saturation is not super saturated, you can see the droplets being formed. Okay, that's how it happens. In the cloud, like it is not hugely super saturated, but you have the little seeds in there. As a result, the droplets will be formed, and then it can grow in the size. There will be a little bigger size because you already have a parent particle on which it will settle. But in the process in the atmosphere, we call it aging. These particles, even if they are smaller, okay, what happens is they come, they agglomerate and they coagulate, and they tend to come more onto this side, okay, with time. So if you are very close to a source, let's say that close to a power plant and emitting at the ground level, you might find a lot of distribution like this. You move few kilometers from there, and then you can find this one, okay. And then this, of course, is the other mode which will be there already. Okay, let me go to this. See, what will happen, okay, these particles can coagulate, okay, but these particles don't coagulate. Whatever the distribution you get in they are there. So what will happen as you move little away from the source, what will happen? This trimodal distribution, as you see, this eventually becomes something like, okay. Therefore, all our studies in air pollution, what we do, generally we are dealing in the fine mode, that is up to something it will come close to 2.5. Okay, so there are distinct things you will get in the atmosphere. So therefore, all the standards that we have been talking about, all the people that we have been talking about, is that, okay, particles with PM10, okay. Why PM10? Although you will get the size distribution like this, but beyond that, the air pollution effects are not so significant, okay, because these are mostly stopped at your nasal cavity and things like that. PM10 can go to the upper part of the respiration system, but these particles, okay, so these become very dangerous. So what you see here is all the time that people can ask you, why 2.5? What is so specific about 2.5? Where this 2.5 number has come? So my idea is that you should always know the simple basics, equations anyone can solve, okay, but then you should know the physics. And you see here why this particle with 0.001 ultrafine, eventually as you move away from the source, it will become something like this and almost dying down here, and then it is picking up here, okay. So therefore it becomes very important to study the fine particles of the origin which has largely come from the gaseous vapor or from the processes, combustion process. And in fact, these things are not so harmful at all. Okay, we have been living in the northern part of the country, tropic conditions, dust storm is a norm for us. Okay, so why should we? I mean, that's how we live. Okay, you go to Rajasthan, you know, in the month of March, April, the dust is everywhere. I mean, you know, like no one cough and no one kind of get worried about it. But this, you look at these particles, okay, come from the diesel and other sources. They are the matter of serious concern. So that is how the trimodal distribution eventually become bimodal distribution, and that is how the issue of PM 2.5 comes in. Okay, it's because that the two modes, and that's why sometimes we use the cascade impactor to differentiate between 0.25 and 10. Something similar kind of graph as you go away from. You remember we gave this range as a name as a course between PM 2.5 and PM 10. Okay, ultrafine and this and that. Okay. If you look at the characteristics, okay, this will be all in the like the sulfate, nitrates, you know, these are the mostly sulfate, nitrate, ammonium, not from the soil. They have all been formed in the atmosphere. Okay, and these are typical composition. You'll get lots of silica in the soil. Calcium is there. Must be aluminum. Must be there. Aluminum is there. So they are more like on the larger particles, the soil dust, and that is there. But these are the primary and anthropogenic secondary particles. They are the quasi-natural kind of thing. So so when you do the study of this chemical composition, you can almost say where the particles have come from. Okay. So if suppose you are getting this level, these levels are much higher, it means the particles are mostly secondary origin and their finer fraction is large. And we do this kind of studies, but this we have done, this will skip. Okay, this is very important, and we'll finish this one. How the particles are formed, especially the smaller particles. The larger particles we know, the one is that the way they are formed is the physical attrition or mechanical dispersion. Another is from the combustion particle burnout, another homogeneous and heterogeneous nucleation and droplet evaporation, and you'll understand because fortunately we have good pictures coming up for you. Okay, physical attrition, these are the large particles that can be formed in the industrial processes. This is the grinding machine, basically grinding wheel. Things are being grinded, very common thing, especially any ore processing to begin with, the grinding is done, and then you see the little particles falling off, and then you are collecting with the fan, and these particles will be the large in the size. If you don't mention here, it will be shown in a moment. They occurs when the two surfaces are rubbed and yields the small particles that break off from both surfaces. So the composition and densities of these particles are identical to this material. Okay, so that won't change. So this is one way. The second thing is, second way the particles are formed is, okay, there are more kind of crushers are there, but they are not being shown. Combustion particle burnout. This is important to understand. Why the fly ash is generally much smaller than the coal that we are firing in? Because the particle is completely burnt out. Okay, as combustion progresses, the fuel particles, which may be larger, okay, they started as 10 to 1000 micron particle from the coal mill, okay, are reduced to ash, and they char particles that are primarily in the range 1 to 100 micron range. This mechanism for particle formation can be termed as a combustion particle burnout. Okay. Well, I don't know if you have the figure here. When the combustion particles burn out and the nucleation occurs in a fossil fuel fired boiler, nucleation is discussed a little later in this section which we have here. So this is we're just talking about the particle burnout and everything together here. So once you are firing the particles here, it can be this is the air which you are firing. The particles may be much larger here. Okay, the location of the volatile, and then immediately the organic matter on some of the metals, okay, for example mercury, will quickly evaporate, okay, where some metals won't, okay, but mercury, in fact lead also to a large extent will evaporate, okay. Then the cooling is there, and then separating the location where the most nucleation occurs. The moment the temperature drop, some nucleation can occur here, right here, okay, and Largely it is talking about the nucleation which can occur right inside the process. Okay, so this is because this you see here you need certain temperature. With that temperature, suppose the burnout is not complete, the vapors will continue to go up, and the vapors, now there is no opportunity for vapors to be burned out, so the vapors escape and then they become, through the nucleation they can become the particles. And this is something, nucleation, you should understand. Maybe we will talk again in the next class. There are two kinds of nucleation. One is a heterogeneous nucleation and one is homogeneous nucleation. Here for heterogeneous nucleation you need already some parent particle, okay, on which the nucleation of your vapors, that is your material 1, should occur. Okay, and then if you don't have the material 2, so then the homogeneous nucleation can occur. For homogeneous nucleation to occur, the supersaturation level have to be way high, otherwise that won't happen. And this is what is the thing. Another thing, maybe some of the coastal area, okay, the natural resources, also find out the droplet evaporation, because you see somehow the water droplets may escape from the sea or something with some operation, and then the moisture, it evaporates, and leaving beside it's a dissolved solids in the atmosphere, which will be very, very fine particles. And same thing, you will be surprised that we use a lot of scrubbing systems for treating the suppose I am entering SO2 here, okay, and I am using spraying something that can dissolve the water, dissolve the SO2, okay, maybe slurry of calcium carbonate, okay. So after this thing, there will be few the mist particles that will emit out, okay, and at the source, like this is the source, okay, and as they emit out from here, you can see some of the particles coming, which sometimes maybe looks like little water or something like that, but eventually the water evaporates and it leaves lots of particles in the atmosphere, which are dissolved in the water spray. So that is another source. We'll discuss a little bit more details of this thing in the next class, but you can see the mechanism through the combustion. The burnout is a different thing, nucleation is a different thing, and drop evaporation is a different thing, and ordinary mechanical crushers, that is a different thing. And that will all give you different particle size. And if some particles are formed through the chemical reaction, that will always be very, very fine. Okay, we'll stop this one here. We'll stop here. Okay.